Okay, last video for this week, Friday. 2.2 though, finally out of 2.1. What we want to do is basically want to kind of realize that we can do the same thing we've been doing with finding the derivatives analytically. We can find the derivatives graphically. And again, I already did a couple examples like this because it kind of shows up in 2.1. But 2.2 is literally this idea. If this is the graph of f, what would the derivative have to look like? Now there's 4 steps to the process, okay? First you want to figure out when the derivative is 0. So you look at the graph here, you realize the derivative will be 0 right there. That is important. When the derivative is 0, it's kind of important to us. You can see here that the derivative or the slope is going to be 0 right there. The slope at a point. The derivative, the slope is actually 2 points. The derivative at one point, or the slope at one point is called the derivative, right? So at that one point, when you said the slope at a point, which is called the derivative, is 0 there. So what I know is, I don't know a whole lot about this graph. I don't. But what I do know is the derivative. Now when I graph the derivative here, the derivative has to be 0 there, right? Remember, the numerical value of 0 means at that point it's got to be 0. Now, notice that's the first step. And the second thing you're going to do is you want to notice when the derivative is positive and when the derivative is negative. Because if the derivative is positive, it's got to be above the x-axis. If the derivative is negative, it's got to be below the x-axis, okay? So notice here, now, I do this, but you don't have to. Notice that when the graph goes down, its slopes are negative. When the graph goes up, the slopes are positive. So when the graph goes down, the derivative is negative. When the graph goes up, the derivatives are positive. So here, notice that since the graph is going down, that means that the derivative is negative. And then here, it's going up. Now, it's going up fast at first, and then it slows down. It's just kind of like a logistical curve, but it's positive. So what does that mean to us? That means the graph is going to have to be down here, and then the graph will have to be up here. Now, that doesn't tell us a whole lot, really. The graph has to go from here to here. Now, we want to make it a little fancier than that, right? We don't want to just like do that. And then the next one, I'm going to switch colors here. We're going to learn later on, this has a lot to do with what's called the second derivative, but don't worry about that for right now, okay? When will the derivative be at its greatest or its least? For right now, where that's going to happen is where it changes concavity. And we'll talk about why. Concave up versus concave down. So notice that this is what we call concave up. And then again, sometimes students panic. Like, where is it exactly? Just guess. It doesn't have to be perfect. Somewhere around here, it changes concavity. This is called concave up, and this is called concave down, okay? Now, why is that important? Watch. Here, the derivative is 0. Then notice that the derivative gets bigger until here, and then goes back to almost 0 here at the end, okay? We'll talk about the end later. But right there, what we notice is that point is going to be the biggest positive value. So here's the thing. I don't care where you put it here. It's got to be positive. You can put it here. You can put it here. I don't care where you put it. But once you put that dot down, that's got to be the biggest one. Because then it goes back to 0 after that. Now, so that's the third step. Now the fourth step is the endpoints. No, sorry, the ends of the graph. At the ends of the function, the graph here. So what you want to ask yourself is, what are the derivatives at the very end here? And it's negative, but it's a big negative number. It's almost infinity there, isn't it? So it's got to be a big negative number. So you got to kind of want to put that down. There's got to be that's a big negative number. So when you drop that down here, it's got to be negative. We know that. It's got to be a big negative number. And over here, it's almost 0. But remember, it's positive. So it's not 0. So when you drop this point down, it's got to be almost not quite 0. It's got to be slightly positive. And then now what you want to do is want to kind of connect the dots. Connect the dots. I'm going to move this over just because I think it'll look prettier. Just making it look pretty as possible. Just kind of connect the dots. Now, what will I be looking for? It better be negative when it's supposed to be negative, and positive when it's supposed to be positive, and 0 where it's supposed to be 0. And it better be at its maximum where it's supposed to be maximum, and the endpoint should be close to right. So that must be what the derivative of that function looks like. The derivative of that. Okay, so let's do a second one here. 5-step process to these. Okay? 5-step process to these. First step, figure out when the derivative is 0. Derivative's got to be 0 here. First step. Not much, but something, right? And then second step, figure out when the derivative is positive and when the derivative is negative. It's going up and then it's going down. So that means the slopes are positive and the slopes are negative. So positive to negative. Now that doesn't tell us a whole lot, but it does tell us the graph has to be in this quadrant and then it has to go down in this quadrant after it passes through 0 there. So we don't know a whole lot about this function, but that's kind of what we know. Then the next one is when we'll be at its greatest and its least. Those are what, right now, for the lack of a better way of saying it, they're going to be at what's called the points of concavity. Concave up, concave down, concave up. Now make sure we talk about y. Derivative is almost 0 at the end. But when it reaches that point there, it now goes back to 0 again. So that point is the most positive it's going to be. I don't care where you put that point, but once you put that point down, that's got to be the most positive. There's a special name for that. It's called the inflection point. Okay, the inflection point is where it's going to be. The derivative will be at its most or its least. Because over here, notice the derivative is 0, but then it's a big negative number, and it goes back to 0. So the most negative it's going to be is down here. Again, I don't care where you put it. So that's the third step. Then the fourth step is the endpoints. So the first step is when the derivative is 0. The second step is when the derivative is positive and negative. The third step is when the derivative is going to be at its most or its least. And the last step, notice at the very ends, the derivatives are almost 0. But they're almost 0 but positive. So I can't put it at 0, I got to put it a little above. Almost at 0, but it's going down, so it's negative, so it's got to be here. And then now you just connect the dots. Try to make it look pretty as possible. Now, you keep hearing me say, I don't care where you put the dots. You guys, this dot here, I don't care where you put it. You could put it here for all I care. You could put it here for all I care. It might look like this to you. Now don't do it twice. I'm just trying to point out that when I say I don't care where you put the dot, but once you place that dot, it's either, once you do that third step where you're placing the derivative at its greatest or its least, you've got to realize that you can't change it after that, right? You know, that's got to, once you put it there, that's got to be the least. Once you put it there, it's got to be the most. Okay, last one. This one is not hard, but it kind of throws people for a loop sometimes. Sometimes when there's not hardly any information, it's kind of hard to figure something out. Notice something that's kind of weird about this function. This was called a monotonic function. It's always going up. Monotonic means always going up or always going down. It's just never. It's always doing one or the other, right? It's not going up and down. The other ones go up and down. Why is that kind of sometimes frustrating for students? If it's always going up, it's never going to have a derivative of 0. Well, because it's always going up. If it's always going up, the derivatives are going to be positive all the time, right? Sorry about that. Got sideswiped by something. Okay, so now, it's always going up. So here's the weird part. It's never going to be 0, and the graph has always got to be, the derivative has to always be positive. So the graph is always here. The graph is always there, isn't it? Well, if the graph is always there, then that doesn't tell us a whole lot. Well, let's see. Okay. So the first step is to check and see whether the derivative is 0. It's never 0. The second step is to determine when it's positive or negative. It's always positive. So almost like it's like lack of information in a sense, right? So now, then the next step is the point of what we call inflection point, or where it changes concavity. Here's concave up, and here's concave down. So right there is, notice the derivatives are 0, the negative derivatives are big, and then they're back to 0. So they're going to be the biggest here. I don't care where you put that dot, but once you put it down, that's got to be the biggest. Last but not least, notice at the ends, it's almost 0. Notice at the ends, it's almost 0. And then now you just connect the dots. Just connect the dots there. Okay, so there's some examples like 2.2. Basically, it's like 2.1, except we're doing it just with graphs, not doing any analyticals. Okay, I'll talk to you later, end of the week.